This is the beginning of module 2 of my control systems course, and it's mainly about the transfer function. Transfer function is central to control systems. It's just a central concept of the whole course. But before we get right there, we need to talk a little bit about Laplace transforms. I'm only going to briefly talk about Laplace transforms. It's in my NMath A course, which is another whole series of YouTubes and materials on my website. But here's the definition of a Laplace transform. You don't have to worry too much about this, but it's an operation on a function of t, where for us t is time. The operation is defined this way. You take your function of time, multiply it by e to the minus st, and integrate that from 0 to infinity over t. So s is some complex variable. Integrate all the t out of this, you end up with a function of s, the Laplace variable. So you have a function of time on the left, a function of s on the right, meaning they're a transform pair. We call this the time domain and this the Laplace domain. Who cares? We care because we use it to solve ordinary differential equations, and it makes a lot of stuff in controls more convenient. Mainly because of this derivative property. The Laplace transform of the derivative of a function is s times the Laplace transform of the function itself minus some initial condition. And if I want the Laplace transform of higher derivatives, it's, to the nth derivative is going to be s times to the nth times the Laplace transform of the original function, minus all these s's times some level of initial condition. And the beautiful thing for us is a lot of the times we're going to be starting in equilibrium and at rest. So all these f at time 0 and f dot at time 0, all these initial conditions become 0, so that the derivative in the time domain just means multiplying by s to that however many power, that many derivatives power in the Laplace domain. So you take a differential equation like this, which in our case earlier modeled a mechanical system, a mass spring damper system. Each derivative you just multiply by s times the Laplace transform of the signal y. So this second derivative, s squared, first derivative s, no derivative, just 1. Which gives us this times the Laplace transform of y. And on the right side is the Laplace transform of the forcing function. We're talking about Laplace transforms of the input and the output y. Do a little bit more algebra on me. Kind of lost, okay, I'm back. We'll divide through by this little parenthetical quantity here. I'll have y and divide through by r. I'll have y over r equals 1 over this parenthetical thing. We're going to call this ratio the output y over the input r, g of s r, that we call that the transfer function. That is the transfer function. We like to get it monic in the denominator, meaning the coefficient of the highest power of s is just 1. So in this case, we'll divide through by m, top and bottom. So here's our transfer function. It's a polynomial in s over another polynomial in s, and the denominator is monic. That is the transfer function, fundamental concept. If you go back to our electrical circuit problem, here was the differential equations. This described how the current worked, and this described the output, the equation for the output, this voltage across this capacitor. The modeling of this is in a previous video. But now let's take the Laplace transform of everything. Take the Laplace transform of this input, E, move all these minuses guys to the right. First derivative will be an S. No derivative here, so it's just whatever the Laplace transform of this little I is. And then the Laplace transform of an integral like this is 1 over S. Group all this stuff together, and you get all this stuff times the Laplace transform of the current. And then the output is just this. You do a little algebra, and you get this transfer function. Output over input is this transfer function, which is just a second order transfer function, mathematically equivalent to the mass spring damper system. And if we go back to that no spring example, which was also a system without equilibrium, this was the differential equation. Take our Laplace transform, you'll have an S times big V here, just 1 times big V here. The transfer function is this guy, or getting this denominator in monic form, this guy. And by the way, we're going to start defining some terms here. So we define the transfer function. It's that ratio of output over input in the Laplace domain. And the characteristic equation is that denominator set to 0. So this is the denominator for this mass damper system above. This is the, did I call it the denominator? This is the characteristic equation for the mass damper system. And this is the characteristic equation for the mass spring damper system. We had an assumption there that said we can, all those initial terms are at 0 if the system starts in equilibrium and at rest. So someone could ask, what if it doesn't start at rest? Well, let's take a system here. Here's a differential equation. Now it has initial conditions on this y, the output, what we're interested in. Times 0, y is some number, y sub 0, and its derivative is some v sub 0. We'll say that this r is 0 for time less than 0. If you go through what that is the long way, using all those initial conditions and that property of the Laplace transform, you get this for the output. And if you look at this part, it depends only on the initial conditions. And if you look at this part, it depends only on this input R. You can separate it. So we didn't really need to assume the system starts at rest. We just say we're looking at this part of the output, knowing we could always just arithmetically add this part of the output if we did some more work, part that's due to the initial conditions. So how much further do I want to go on this guy? About 2 more charts. So if we have any 2 of these 3 guys, we can get the third. If I have the output and the input, I can identify the system, the transfer function. By the way, system, I taught signals and systems, and in the last week of the course, a student asked me, what is a signal and what is a system? Well, a signal is just a sequence of numbers. Usually we mean a continuous sequence over time, a function. A system converts an input signal to an output signal. That's all it is. So this system, or the transfer function, tells us how this input signal gets transferred to an output signal. The output is just this product, transfer function times the input, all in the Laplace domain. And if I wanted to know the input given the output in the system, or the transfer function, it's this. Give me any two, I'll get the third. To get what they are in time, you got to take the inverse Laplace transform. That's the idea of a transfer function. It converts inputs to outputs in the Laplace domain. Poles and zeros, we'll define them. They're other big concepts in controls. I said the transfer function, it has a numerator and a denominator, right? Set the denominator equal to 0, that's the characteristic equation. The roots of that equation, the s's that make that statement true, are called the poles of the system. If you set the numerator to 0, the roots of that equation are called the zeros of the system. It's going to turn out we can find out a lot of the dynamic behavior of the system just by knowing where the poles and zeros are in the complex plane. And we'll get into this later. Characteristic equation, poles, zeros, and the transfer function itself. Those are all important definitions and concepts throughout this course. That's where I'll stop.